Now we're going to learn in chapters 4 and 5, we learn basically two things: how atoms combine to make compounds, and then how to name them. There were some other things in there, but those are the main ideas. And now we're going to learn what we can do with that information. That's why we call it chemical calculations. First, we're going to determine what molar mass is. Then we're going to determine what moles are, then molar mass, and then equations and balancing equations is required. Okay, so let's get on with it. So we used to call it molecular mass because the formula was this, and we treated it as a single entity. But we know that ionic compounds don't form molecules. So that's why we now refer to it as formula mass. Just what mass is assigned to that particular formula. In this case, we have 10 2-fluoride, right? Why did I call it that? Because fluorine always has a -1 charge, right? And if there are two of them, we got to balance that with just one of these. So that's why I called it 10,2-fluoride. And the other reason that I stuck that in there is because of where 10 is located. All right, it's a metal, and it has potential for more than one charge. So we use the type 2 convention. We have to say what the charge is. Okay, so we're going to start off identifying formula mass as just how much in atomic mass units does each one of the atoms in the formula weigh. And then if you add them all together, that gives you the mass of the formula itself. Now 10 is 118.71. Yeah, I can actually read that from here. And fluorine, you need two of them. And they rounded off to 2 decimals, they're 19. So 2 times 19 plus 118.71 is 156.71 atomic mass units. That's if you had one 10 atom and 2 fluorine atoms. That's what they would weigh, that many atomic mass units. How about sulfuric acid? Can we calculate that? How much does hydrogen weigh? Got your periodic tables? Rounded off 2 decimals. Say what?
0.
1 point what? 1.0. Give me another decimal. Okay. And that's times 2. Right? How about sulfur? I think sulfur's in the neighborhood of 32, isn't it? Point.
0.7.
Okay. That's just times 1. How about oxygen?
16.
Times 4. All right. So then we add those up. This will be 64. This will be 32.07, and this will be 2.02. So we just add them up. 9, 0, 6, 7, 8, and 9. 98.09. They rounded it off. All right, they chopped off the last 2. So that's the atomic mass units for 2 atoms of hydrogen, 1 atom of sulfur, and 4 atoms of oxygen. That's not very convenient in the lab because we don't have any balances that weigh in atomic mass units. So we need a unit of measure that's massively bigger than that. Because we know that if we have just I don't know, just this marker, probably got billions and billions and billions of atoms in it, but it's large enough for us to put on the balance and weigh it. So we need a huge number of atoms for our unit of measure. And that unit turns out to be 1 mole. 1 mole, and that's the abbreviation for mole. MOLE is the whole name. MOL is the abbreviation. Figure that one out. Okay. In our case, things is atoms. Or it could be molecules. Or it could be formula units. Doesn't matter. Right? Since we're in chemistry, we won't use chickens. This is to 4 significant digits. Now, it's based upon our standard unit for atomic mass units is carbon 12. Remember that one? We did that, didn't we? We didn't do that? Okay. The standard is carbon 12. Carbon 12 is equal, by convention, 12.0000 atomic mass units per atom. Okay, that isotope. Everything else is based on that. The reason that we choose this number is because if we have 1 mole of carbon atoms, this is per atom. If we have 1 mole of carbon atoms, then we also can say grams per mole. That's why we use this value, because it gives us the same number in terms of grams per mole. Different units of measure, same number. So any value that you read of the periodic chart as the atomic weight of that element, it takes into account all the isotopes that are naturally occurring in our environment and gives you a fractional value. Even carbon has a fractional value because it's a weighted average of carbon 12, carbon 13, carbon, I think 11, and a bunch of other isotopes. But it means 2 things. It either means atomic mass units on average for an atom, or it means grams per mole. And that's the one that's more useful. Okay. Now, over time, new periodic tables come out every 10 years or so, and they adjust the values for that atomic weight. And the adjustments are usually in the 6th, 7th, 8th, 9th decimal place. So if we limit our the calculations to just the first 2 decimals, we can use periodic table that's 50, 60 years old and still be fine. All right, how many eggs does 1 mole of egg contain? That number. Oh, they chopped off a 2, didn't they? So this has a special name. It's called molar mass. Well, it's not that special. It's the mass of a mole of those atoms, or the mass of the mole of those molecules. So if we have a mole of nitrogen atoms, then we'll also be able to weigh that mole on the balance and get 14.01 grams. If we have a mole of carbon dioxide, then all we have to do is like we did before with the atomic mass units. Carbon dioxide then is going to be 12.01 for carbon and 2 times 16 for the oxygens, 44.01 grams per mole. Okay. And since, let's see. Yeah. Since 44.01 grams is equal to 1 mole of CO2 atoms or molecules, remember, with an equivalence, we have a conversion factor. We can use it like this, grams per mole. If we have, say, we have so many moles, X moles, and we want to find out how many grams that is. If we have the molar mass of that X, then we just use it like this. And that'll give us grams. But since it's a conversion factor, if we have so many grams of X, then we can use that same value, only now we put grams on the bottom and moles on the top. Because remember, conversion factors, all of them are equal to 1. So when you flip them, still equal to 1. All right. So what would be the mass in grams of 2.5 moles of ethane, C2H6? Well, if we're starting off with 2.5 moles, and we want to find out how many grams, that means grams has to be in the numerator, moles in the denominator in order to cancel. Anytime you've got grams and moles as a quotient, whether it's this way or inverted, think molar mass. So what's the molar mass of C2H6? The hydrogen is easy, 6.06 for all the hydrogens, right? And then 2 carbons would be 12.01 times 2. All right, so we have 8, 0, 3, 30.08 grams per mole. 2.5 times 30.08. It's probably animated. Let me see. Yeah, there it is. All right. 30.07. They must have looked it up in a chart instead of calculating. But we end up with about 75 grams. Of ethane. You need to become familiar with these calculations, because when we start working with chemical equations and trying to determine what's the outcome, when you're given a certain amount of reactant, how much product can you expect from that reaction? You need to be able to make that conversion. And I'll show you exactly why in a few minutes. Number of moles in 50 grams of water. So if we have 50 grams of water, we want to convert to moles. So what's the molar mass of water? Well, let's see. Oxygen 16, right? Hydrogen, 2 hydrogens is 2.02. So 18.02. Like that, 18.02 divided into 50 should be animated 2.78 moles. Okay. Now, just because this problem gives you a bigger molecule, like aspirin, doesn't mean that you don't follow the same rules, right? C9H8O4. Aspirin, everybody ever heard it called acetyl salicylic acid? No, that's what aspirin is. So let's see, is it going to animate for me? No, it's not. But all you need to do is 9 times 12.01, 8 times 1.01, 4 times 16, add them together. That gives you the molar mass of aspirin. And then you take, and since it's 1 mole, that's all there is to it. It's just 180 grams. Now, why did they put 325 milligrams in there? Anybody know? 325 milligrams is the standard dose of one aspirin. I think that's, what is that? I think it's 5 grains. They used to call it 5 grains. 325 milligrams is standard dose. You might know the standard dose for baby aspirin? No? It's 81 milligrams. Little tiny things. I take one every morning. Just to keep my platelets from sticking together. Come in. Let's see. I think I've got a paper for you.
We did a picture view.
No, we're doing chapter 6. We're not going to meet next week because I have to be out. So you do the review in the video. So, all right. So when we write the formula, we've already done this for names. We know that the subscripts can mean, for a formula, the subscripts can mean that many atoms, right? That position, the lower right-hand corner, is one interpretation is number of atoms in that formula. So this one would have 2 atoms of nitrogen and 4 atoms of oxygen. But it can also mean 2 moles of nitrogen and 4 moles of oxygen in 1 mole of dinitrogen tetroxide. Okay. I think it's also called hydrazine. Okay. There's 2 ways to look at it. If you're going to do calculations, the second way is better. So how many moles of carbon atoms and hydrogen atoms are present in a 2.5 mole sample of C2H6? Well, if we have 2.5 moles of that formula of our ethane, then 2 times 2.5 is 5 moles of carbon, and 6 times that is what? 12 plus 3 is 15. Yeah, 15 moles of hydrogen and 5 moles of carbon in 2.5 moles of that formula. Okay. If you have that formula, right, should look something like this. With our hydrogens here, 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 and here, like that, that. If you have 1 mole of that one, and it all of a sudden just breaks apart, all the bonds are gone. What do you got now? Well, you got 6 hydrogens out of 1 mole, so you got 6 moles of hydrogen, and you got 2 carbons, 2 moles of carbon. That's what we're saying. All right. So in this formula for aspirin, how many moles of carbon atoms, hydrogen atoms, and oxygen atoms are present? Well, it's obvious. The subscript tells you how many. Right? If you have 1 mole of that formula, you got 9 carbons, 8 hydrogens, and 4 oxygens. That flow chart. If you like flow charts, I took this out of your textbook. It's probably going to be better if we just work the problems. What I'm saying in that bottom part is if you know what you're given, you know what the target is, then you can deduce what your conversion factors need to be. And once you know what the conversion factors need to be, then you can go either look them up or calculate it. So this is a problem I give all of my students, right? Because everybody's gone on a road trip, right? What do you need to know? Probably is the most important thing you need to know before you go on a road trip. How much money do I need? Right? How much money do I need to get me there and back? And we're talking about gasoline, right? Okay. So I used to drive more regularly than I do now, but I would go from Beckley to Atlanta because that's where my sisters live. And now my brother lives there too. He retired from American Airlines. He was actually a captain. So there is a Captain Bly in his family. And if I know how far I'm going to drive and I know the mileage of my car, then I can calculate how many gallons I need. And then I need to take an average value for the cost of gasoline and factor that in. I can find out how much money I need to get down there and back. And then I usually pad it with 10 or 15% for driving around. So what we would do is we would start off, we're given, it's 385 miles from my house in Beckley to my sister's house in Covington, Georgia, just outside of Atlanta. All right. If the target is dollars, we don't have a single conversion factor that will take us from miles to dollars. It doesn't exist. So if we have 385 miles that we have to go one way, and we want to end up with how much is it going to cost? Sometimes I work backwards. I know I'm going to be driving. So the cost is going to be gallons of gas, right? If we're going to have dollars here, that means this conversion factor has to have dollars in the numerator. And then gasoline is going to be so much per gallon, right? Well, now we need a conversion factor that will cancel that gallon and, leave me with gallons. That's right. Leave me with gallons here. And the next conversion factor is mileage on your car. To make it easy, just say something like, actually, I got close to 30 miles a gallon on my Highlander. That's amazing. So we'll use 30. 30 miles per gallon, per 1 gallon. There we go. I think we got it. We just need to know what is this going to be. I always have just barely enough gas to get to Withville because the gas is like 30 to 40 cents cheaper per gallon just across the border in Withville. So on average, but then I got to go to Atlanta and there the price goes back up. So on average, what nowadays, I don't know, $3 a gallon, probably be rough. Okay, so gallons cancel, leaves us with dollars, miles cancel. So now we've done all our thinking. The rest is number crunching. 385 times 1 times 3 divided by 30 to give you a value. And that's just one way. So I need to double that to get back. And for driving around, I usually just pad it with 10%. Okay. That's how we use conversion factors. All right. That must have been some time ago. Closer to $50 now. So I need about $120, $110, $120. Maybe I better make it $130. Atlanta's a big place. Takes you 15 or 20 minutes just to go to the grocery store. All right. So which of the following is closest to the average mass of one atom of copper? One atom of copper is not going to weigh 60, 50 grams. That's just pie in the sky. Well, I'll just say it's stupid. You're not going to have one atom that weighs that much because the atoms are not that big. Right? So logically, the last one would be the correct answer. But the way you calculate it is not shown. So we start off with one atom. We want to find out what its mass is in grams. So what conversion factor gives us grams that we've learned so far? Molar mass. Right? So grams per mole. Copper is 63.55, I think. Right. Now, we got to cancel moles. Now we do have a conversion factor for atoms and moles. Right. 1 mole, 6.022 times 10 to the 23rd atoms. Avogadro's number. I didn't mention that before. Avogadro's number, Avogadro is credited with this, but he never actually calculated it. It's just that Avogadro's theories and his work in that area made this unit of measure possible. So his name was attached to it. All right, so now we got atoms. So all we have to do now is say 63.55 divided by 6.02 times 10 to the 23rd. And that should be 1.055 times 10 to the minus 22 grams. All right. 23 is in the denominator. When we bring it into the numerator, or when we divide with it, we're going to get a large negative value of power of 10. So this is a trick question. How many atoms are in 63.55 grams of copper? Well, the short answer is 1 mole. The long answer is 6.022 times 10 to the 23rd atoms, because that's equal to 1 mole. Okay. All right, step it up a little bit. Say we have a 100-gram sample of each one of these: magnesium, zinc, and silver. We got 100 grams of each one. Okay. We want to know which one contains the greatest number of atoms. If you've got the same mass, how do you get that mass? You add up the masses of all the atoms, right? So if you've got a heavy atom, it takes fewer of them, right? And if the lighter atom is going to be the one with the most number of atoms required. So all we need to do is compare the molar masses. Magnesium is, we could just estimate 24.3 grams per mole. Zinc is, get a little closer, I can see it. Oh, reflection's too bad. Somebody has to tell me. What's the molar mass of zinc? Can't find it. Are you looking at the periodic table? Okay.
65.41.
Okay. And silver.
107.87.
Okay. So the lightest one is this one. That means it's going to take more atoms of this one to give you 100 grams than it does of this one or that one. And the fewest number would be this one. Then say put them in order, just say the greatest number. Okay, the greatest number is going to be magnesium. Okay. Okay. Now, we're going to complicate things even further. I'm going to leave those there. Silver. Actually, silver is this many grams, 107.9 grams. And zinc is given to us as 70 grams. So we're not 100 grams anymore. We have different masses for each one. And magnesium is 21 grams. Okay, if we're going to put these in order, we just need to know what's the relative number of atoms for each one. That's 1 mole, isn't it? This is greater than a mole. And that's less than a mole. So now we can put them in order from descending number of atoms, from the greatest number to least number. So greater than 1 mole is zinc, then 1 mole is silver, and then the last one is less than a mole, magnesium. So it should be zinc, silver, magnesium. Yep. Okay. The slide actually gave you the values, but in order to put them in order, if you want to put them in order, all you have to do is find out what's their relative positions relative to a mole. Okay, this one, we get more and more complicated. This one's going to need Henry Ford assembly line. So if we've got water here and dinitrogen monoxide, that's laughing gas, nitrous oxide. C3H6O2 is probably propionic acid and carbon dioxide. And we got 100-gram samples of each one. See, I'm setting up an assembly line. I'm going to treat these things. The calculations are exactly the same. It's just that some have windshield wipers and some don't. That's not a good example. Some have stereos, some don't. So you need different factors. We're going beyond Henry Ford, actually, because what did Henry Ford say about his cars? You can have any color you want, as long as it's black. Okay, so we need to, what's the question? Number of oxygen atoms. Right, we can't tell from this the number of oxygen atoms because that's the mass of the whole molecule. But if we find out how many moles of the molecule there are, then we can introduce another conversion factor that will give us the number of oxygen atoms. So it's a two-step. Right, we're going to cancel grams, put those on the bottom, give us moles. This is moles of molecules. All right, so water, we did that one earlier, 18.02. Dinitrogen monoxide, how about that one? 2 times 14.01, 28.02, and then oxygen, 16. 2044, 4402. Right. How about propionic acid? Let's see, 3 times 12.01, 6 times 1.01 for hydrogen, and then 2 times 16. All right, then we add those up. Let's see here. 12.01, oops, start over. Times 3. That's 36.03, and then 6.06 for the hydrogens, and 32 for the oxygens. So I get 7409. Okay, and carbon dioxide. That's 12.01 and 2 oxygens. Right. 32 and 12.01. 44.01. Okay. So now we have our conversion factors for the number of molecules. So if we have 1 molecule of each one, how many oxygen atoms do we have? For this one, it's 1 to 1, right? For every mole of the formula, we have 1 mole of oxygen. So it's 1 to 1. Same for this one, 1 to 1. This one is 2 to 1. And carbon dioxide is 2 to 1. All right, so we've done all our thinking. Now it's just a matter of calculating the values. All right, 18.02 divided into that is 5.55 times 1. That's moles of oxygen. That was the question, wasn't it? Number of descending order of number of oxygen atoms. We don't have to go all the way to the numbers of atoms. Right? If you're just going to put them in order, moles will work fine because that's a counting unit of measure. Let's see. 4402 times 1 is 2.27. Okay. And then 74.09 times 2 this time is 2.70. And 100 divided by 44.01 times 2 is 4.54. Okay, so if we put them in order, descending order. So the most is this one. Then the next one, then the next one, the next one. Okay. Oh, I didn't animate that one. Oh, maybe I did. Descending order of number. I did. Okay. So there's the first calculation. There's the second calculation. So far, so good. Yep. And yeah, off by 100th. Okay, so we put them in order. There they are. Okay. Is that giving anybody the heebie-jeebies? Or just bored? Because you're awful quiet. All right. Let's see. There's aspirin again. Number of molecules in 0.325 grams. That's a standard dose for aspirin. 325 milligrams. And calculate the number of molecules. So if we take grams and convert them using the molar mass of that formula, and then times Avogadro's number, we'll cancel moles and give us molecules. So we've got about 10 to the 21st molecules in a 325 milligram dose of aspirin. If it's fresh, right? You got any aspirin on your shelves at home? Does anybody keep aspirin anymore? Usually Advil or Tylenol. I like to have a little aspirin. If you have an aspirin bottle and you open the cap, have you ever done that? And smell? What do you smell? I'm sorry? No? Oh, I thought you meant an answer. You smell vinegar. The decomposition of acetyl salicylic acid, the acetyl part is turns into acetic acid. It breaks off. Acetic acid is vinegar. You get that smell. So if it's old aspirin, you're not going to have that many molecules, right? It's only going to be salicylic acid, not acetyl salicylic acid. Okay. Now that we're professionals at calculating moles, we're going to go back. We started off, we learned the alphabet, right? About half of the elements on the table, learned the alphabet. Then we learned how to write words, chemical formulas, right? How to name them, how to write them from the names. Now we're going to put them in chemical equations. This is like a sentence. This tells you what's happening in a chemical reaction. Reactants always go on the left, products on the right, by convention. This one has calcium sulfide plus water yields calcium oxide plus hydrogen sulfide. When we balance the equation, we look at how many, you can look at this in terms of atoms or moles, it doesn't matter. How many atoms of calcium are on the left, how many are on the right? And this is in obedience to the conservation, Lavoisier's conservation of mass in a reaction. It's based upon Dalton's interpretation of that with his atomic theory. You have the same mass on either side because you have exactly the same number of atoms on either side of the elements. So calcium is one on the left, one on the right. We're good there. Sulfur is one on the left, one on the right. We're good there. Hydrogen, two hydrogens on the left, two hydrogens on the right, one oxygen on the left, one oxygen on the right. That equation is balanced. That's what we mean by balanced equations. And you can also interpret that as moles, right? So you have 1 mole of calcium sulfide, 1 mole of water as reactants, gives you 1 mole of calcium oxide. Calcium sulfide gives you calcium oxide and 1 mole of and hydrogen sulfide. And we know that because of coefficients. When we write an equation like this, it's understood. If you got the formula there, it's understood to be 1. There's a 1 understood to be in front there. We don't write it because that would be redundant. If the formula is there, you got to have at least one of them, right? Now, if you need more, then you just put the right number there. And that's the way you balance an equation. Once you have written these compounds correctly and put them in their proper place as reactants or products, you can't touch the formulas. You can't change the subscripts to make them balance. That's cheating. So that's what the coefficients do. They tell you how many moles, they tell you numbers of that unit, numbers of that unit, that unit, that unit. The way we've written this, there's 1 of each. And that's the simplest whole number ratio of reactants to products. So for every 1 of these, you get 1 of those. That's an equivalence. 1 of these equals 1 of those. That's a conversion factor. Okay. I think this was the author slide. I don't care too much for it. I think we just need to practice. All right, here are my helpful hints. I added these to the slides show. And you should have a copy of these, hard copy of these that I handed out earlier. Now, we're not going to stop and talk about each one of these hints. We're going to actually use them, right? So we have 2, 3, 4 slides with helpful hints. All right. I'm not going to start off with this one. I want to go to maybe this one, and show you my budget method. Has anybody had experience with balancing equations, maybe in high school? Okay. Was that a stretch or a yes? Okay. Now, I'm not sure how your high school teacher taught it, but I use what I call a budget method. You write the equation with the proper formulas for your compounds or elements, whatever the case may be, and put them in their proper position. Let's see. Yeah, that's carbon yields calcium carbide plus carbon dioxide. Okay. And then down this side, I put the elements that are in the equation. So we've got a calcium, got an oxygen, got a carbon, and that covers all of them. And then we tally in here. First, we say how many calciums are on this side? One oxygen, one carbon. And then on this side, we have one calcium, we have two oxygens, and we have two carbons. Okay. You can see at a glance that this is not balanced. Right? 1, 1, 1, 2, 1, 2, not balanced. So the next thing you do is use the first hint. Helpful hint is if you have an element on either side, anywhere in your equation, do that one last. Don't put a coefficient in front of that one first. Do it last, because if it's in the last step, then you're only changing that one. Right? If you have to put a coefficient in front of one of these last, it changes something else, and then you're back to balancing that one again. So save these till last. So that means we have calcium's already balanced, so we can't mess with that one. We could do oxygen or carbon, and carbon's we're holding carbon to last, so we have to do oxygen. So we have two oxygens over there. We need two on this side. That's how you get two. But we also change the calciums like that. So now that we've got two calciums there, we need two calciums on this side. Right, two there, and that gives us 5 carbons. Sometimes I do an intermediate check. Right, how many calciums do I have? 1, 2. Let's see. We have 1, 2, 3, 4, 5. 2, 4, 5. We have 2, 4, 5, 6, 7. 2, 4. Ooh, that's 9. What did I do wrong? 2 calciums, 4, 5 carbons, 2 oxygens. No, that's 9. I counted these wrong, didn't I? 2 plus 4 is 6, 7, 8, 9. There we go. Okay, so I got all these add up to the number of atoms, 9 atoms. Okay, now we're down to carbon, and we kept carbon for last. So in order to get the right number of carbons, I just need a 5 right here. And we can see it's balanced. And you look for the simplest whole number ratio at this point. There are special cases, and we probably won't get to those in this class, where fractional coefficients are permitted. But we're shooting for the lowest, the smallest ratio, coefficient, whole number ratio. So 2, 5, 2, and 1 can't be reduced any further. Primarily because that's a 1, but also because that's a 5, and the others are even. So it's 2, 5, 2, and 1. And the best answer for that one is Roman numeral 2. Okay? All right, now I'm going to go back to this equation so that I can show you another trick or a helpful hint. And I've animated it so I don't have to draw it on the board. Notice that in this equation, you've got ammonium on the left and ammonium on the right. And it's not broken apart in the process. right? You've got ammonium over there, you got ammonium here, but you don't have nitrogens and hydrogens from that anywhere else in the equation. If that's the case, then you can use ammonium as a balancing unit. And that saves you a lot of headache. So here's my count. I've got ammonium and phosphate is the same way. You can use them as balancing units. So we're doing the assessment first. Checking out how many of each is on what side. Okay. So now that we've added up everything, ammonium, phosphate, calcium, and chlorine are the balancing units. So which one do we do first? All right. Well, I'm going to balance calciums first. All right. That changes the chlorines. So now I need to go on the other side and balance the chlorines. Okay. Now that I've got the chlorines balanced, I've got to balance the ammonia. And now our equation is balanced. And the beauty of this system is you can see instantly whether your equation is balanced or not. Now, this method doesn't work for 100% of all equations, but it'll work for all the ones you're going to get in this class. There are other techniques that we add on top of this to handle some of the oddballs. Okay. Balanced equations, number of molecules is concerned? No, not necessarily. Coefficients tell you how much of each substance you have. When it says how much, they're talking mass. And the coefficients tell you nothing about mass. A balanced equation is working on numbers of atoms, numbers of molecules. Right? You can use them to deduce mass transformations from one side to the other, but the equation itself says nothing about the mass. Atoms are neither created nor destroyed. That one's still true. Yeah. Coefficients do not indicate mass ratios, and the sum of the coefficients on the reactant side is not necessarily equal to the sum of the coefficients on the product side. Right? Only one of those is true. Okay, let's see. We're going to decompose sodium bicarbonate, sodium hydrogen carbonate. And the product is going to be sodium carbonate, carbon dioxide, and water. My general chemistry class, we do this reaction in class and use it for calculation purposes. But in this class, we don't have the time or the expertise to do it. So if you have sodium bicarbonate yields sodium carbonate plus carbon dioxide plus water. If you work the budget method off long enough and on enough examples, eventually you might come to the place where some equations you can do without working the budget. I can say, I need 2 sodiums on this side. Now I need 2 hydrogens. Got them. I need 2 carbonates. Only got 1. Oh, wait a minute. I got 2 carbons here. I've got 2 times 3 is 6 oxygens. 3 plus 2 plus 1. That's it. We're balanced. We just needed 1 coefficient. And we're balanced. Now, I could have laid out that in our budget method, but it would have taken a while. And we only needed one coefficient to fix it. Okay, here's a balanced equation. Just a reminder of what the coefficients mean. For molecules actually 4 atoms of iron react with 3 molecules of oxygen to produce 2 molecules, actually 2 formula units of iron 3 oxide. Did I name that one correctly? What's the charge on oxygen? -2, right? That means -6 total. It means we have to have a +6 out of these two, means each one is +3. So iron 3 oxide is the correct name for that compound. You ought to be practicing those. When we're doing these, practice that, because naming compounds is a perishable skill. Don't use it, you'll lose it. All right. So for that balanced equation, suppose we have conversion factors. 4 moles of iron produces 2 moles of iron 3 oxide. So let's go back to the equation. Let me write it up here. 3 oxygens and 2 iron 3 oxide. How many conversion factors can we get out of this? If you want to convert from this one to this one, right? You have, let's say we have so many moles of iron, and we want to convert to so many moles of iron 3 oxide. What we would need was the coefficient for iron and the coefficient for iron 3 oxide, right? Numerator, numerator, denominator, denominator. Well, cancel. But the ratio between the two is 2 here and 4 there. Okay, that will give you the number of moles of this one. If you want to go back the other direction, all you have to do is substitute this in here and that over here and flip that one. So that gives you 2 conversion factors, possibilities. We can go from here to here, right? There's 2 more, so we're up to 4. We can go from here to here. That's 2 more, that's 6. So out of this equation, you can get 6 conversion factors. It just depends on what you have and what you need. And that's the purpose of this slide. All right. In the equation, ethane plus oxygen yields carbon dioxide and water. We did types of chemical reactions, didn't we? Have we done that yet? Maybe we haven't done that yet. Gases, liquids. No, we haven't done it. Sorry. This is a combustion reaction. Whenever you combine something with oxygen and get products, it's called combustion. So we're adding oxygen to ethane and getting carbon dioxide and water. Anytime you have a hydrocarbon like ethane, carbon and hydrogen only, those are hydrocarbons. You combine it with oxygen, you always get carbon dioxide and water. If it's complete combustion. If it's inside your automobile engine, you might get some oxides of nitrogen and incomplete carbon compounds. Anyway, back to the question. If we balance this equation, what are the mole ratios? All right, so let's do this one. So we have got time. It's a little after 10. Okay, we got till 11, then we have to do the lab. How many more slides do I have? Yeah, I think we're good. Okay, so we have ethane, and we're going to use the budget method. And we have carbon dioxide and water. Notice I leave a little gap here for my coefficients. Okay, so we're going to tally carbon, hydrogen, oxygen. That's it. 2 6, and 2. And over here we have 1 hydrogen, 2, and 3 oxygens. Okay. So we're going to hold oxygen till last. And if you can't decide where to start, just start at the top. We need to balance carbons. So I'm going to put 2 over here. That gives me 2 of those carbons. That also changes the oxygens from 4, 5. Right, now hydrogens. I need 6 on this side. So 3 in front of that hydrogen will give me 6. Right? 6 hydrogens. Now it changes the oxygens again. 3 plus 4 is 7. Okay, now we can do oxygen. How do we get an odd number out of an even number? If I put a 7 in front of that, that gives me 14 oxygens. What if I use a fraction? That's one of the tricks. If I use a fraction as an intermediate step, 7 halves, does that mess with anybody's head when I do that? Think of it this way. This is an oxygen. This is an oxygen molecule. If I have 7 of those, right, but I take half of them, right? If I take 7 of these, but I then take half of those, I've got 7, right? So that's what I've done, mathematically speaking. Okay, now that we've got a balanced equation, the ratios of these coefficients are fixed. So it's like any math equation. If I do the same thing to both sides, like multiply to both sides on both sides, then I haven't changed the ratios. So what I want to do is multiply times 2. 2 times 7 halves is 7, right? 7 times 1, 2 times 1 is 2. 2 times 2 is 4. And 2 times 3 is 6. We still have the same ratio as before. But now we have the simplest whole number ratios. All right, so 2, 7, 4, and 6. 2, 7, 4, and 6 is the proper. And that was the third trick that I showed you. Or hint, if you prefer. So fractions are permissible as an intermediate step. All right. Now we're going to talk about stoichiometry. What do we mean by stoichiometry? And I think we're only going to get just a smidge of, well, we get, actually more than a smidge. Stoichiometry is a big word. It's derived from the German, which, and I can't remember its exact definition unless it's in here somewhere. No, it's not. Stoichiometry allows us to use these balanced equations to say how much product we can expect from the amount of reactant we get. So if we're given so many grams of reactants, we can calculate how many grams of product we get. So there's your flow chart if you want it. This is probably, this exercise is pretty involved, but if we break it down, it's not that bad. We've got 2 equations here. One where we burn methane and one where we burn ammonia in oxygen. So we actually have 2 equations. If we take methane and combine it with oxygen, remember we always get carbon dioxide and water. And then I want to do this one first, and then we'll do the same thing with ammonia. And that gives us, it tells you the products. It gives you nitrogen, monoxide, and water. So let's balance this one first, right? Carbon, hydrogen, oxygen. So we have one carbon, 4 hydrogens, 2 oxygens. On this side, we have 1 carbon, 2 hydrogens, and 3 oxygens. Okay. So carbons are already balanced, so we'll go to hydrogens because we don't want to touch oxygens yet. So we need 4 hydrogens on this side. Put a 2 there. That changes it from that to that. And now we just need to change the oxygens. Right? 2 times that gives us 4. And that's balanced. Okay. Now let's do the second one. Ammonia. Plus oxygen yields nitrogen monoxide and water. So now we do our tally. NH&O, 1 nitrogen, 3 hydrogens, 2 oxygens, and 1 nitrogen, 2 hydrogens, and 2 oxygens. Okay. We're going to save oxygen to last, so let's mess with, here comes another trick. If you've got hydrogen in one place on this side and hydrogen in one place on that side, but the coefficients give you an odd and an even, the best approach is to cross multiply. So we'll do both at the same time. We'll put this 2 over here and that 3 over here, and that gives us hydrogens. That gives us 6 hydrogens on this side and 6 on this side. Okay. But it also changes the nitrogen to 2. And over here, it changes the oxygens to 3, is 4, correct? Did I do that right? Yeah, I think I did. Okay. Now we've got 2 nitrogens over here. We need 2 on this side. 2. So we got 2 there. That adds 2 plus 3 is 5. Okay. Now we can use the trick we've already used. 5 halves gives you 5 here. And then we get rid of the fraction, multiply by that denominator, and that gives us 4 here, 5 there, 4 here, and 6 here. Okay. I know at this point it probably looks like magic. Let's see, I'm going to clean it up. That needs to be 4. Because we're going to use both of these equations. 5, 4, and 6. There we go. So those are our balanced equations. And that should be 4, 5, 4, and 6. And 2 and 2. Yep. Okay. Now the question is, what mass of ammonia would produce the same amount of water as 1 gram of methane? So we're given 1 gram of methane. We want to know how many grams of ammonia will give us exactly the same amount of water. And I'm talking about mass of water. Actually, moles of water will do also. If you've got the same number of moles of water here as here, you got the same mass, right? Oh, was that too much? So how do you get from there to there? Because that's where we have to go first. Then we can say this mass or this number of moles is the same as that moles. Then we can work backwards. Right? So how do you get, remember, think of it this way. There's a great wall in there at each one of these operators. You can't get over that wall. You can't get under that wall unless you're moles. If you're anything else but moles, you're stuck where you are. So this has to be converted to moles. Right? That means we need a molar mass for methane. What's the molar mass of methane? 12.01 and 4.04 is 16.05. Right? So 16.05 into 1. Another name for that is reciprocal. And that key is right there. 6.23 times 10 to the minus 2. 6.23 times 10 to the minus 2 moles of methane. That's what we start with. Now we also, in this case, we have to say this is excess. Oxygen is excess. We have to say that because if oxygen runs out, the reaction stops. It doesn't matter if we've used up all of this or not. So if oxygen is excess, then we can use all of that up. Okay. So we need to convert moles of methane to moles of water. What's the ratio? Well, 2 and 1. So 2 times that value will give us the moles of water. 1.45 times 10 to the minus 1. Moles of water. Okay. If the condition is the equal masses of water, we've also got equal moles. So this number of moles here can go here. Okay? So now I'm going to work backwards. Let's put that in standard notation. 0.145 moles of water. Now we need to convert that to moles of ammonia. So we got water here and ammonia here, right? Does it bother you? I'm going backwards. Okay. So the ratio here is 6 waters to 4 ammonias. So 2/3 of that value is 8.31 times 10 to the minus 2. 8.31 times 10 to the minus 2 moles of ammonia. Now that we know moles of ammonia, we can convert that to mass. So just moles on the bottom, cancel, grams on the top. We need to know the molar mass of ammonia. All right, so nitrogen is 14.01 and 3 hydrogens, 17.04. Right, that cancels moles and leaves us with grams. 17.04 is 1.42. 1.42 grams of ammonia. So what that's saying is, if we burn a gram of methane in excess oxygen, or we burn 1.42 grams of ammonia in excess oxygen, we get exactly the same amount of water with either one. Okay, so there's the animation. Right. Moles of water, then we take moles of water and convert it to moles of ammonia and then grams of ammonia. So that's stoichiometry. The central idea in stoichiometry is first balance the equation and then convert to moles to go anywhere you want to in the equation. If you're not moles, you're stuck. You can't move. In this case, we use grams and molar mass to convert. But you can do it with solutions too. We haven't talked about solutions yet, have we? Units of measure? Okay. We'll save that till later. Okay. This is a dose of reality. If you're a chemical engineer and your supervisor or the company, through your supervisor, says we want to scale up a reaction. Right? First, we got to find out, does the reaction work on a small scale, like on the bench. Then we do maybe scale it up a little bigger to maybe a big table size. Be sure it still works. And then we want to scale it up to production size. But in order to work our numbers, we need to know how efficient is the reaction, right? We just worked out 100% efficiency. Right? All of the methane ended up with water and carbon dioxide. But that never happens in reality. In the real world, it's always less than. So you try to maximize that yield. And that's why the expression percent yield, oops, that was dying on me. Thought I had another one here. Yeah, I do. Percent yield is equal to the actual yield divided by the theoretical times 100. So it's a dimensionless number, right? Because whatever units of measure you have here get canceled here. That's the nature of percent. It's always dimensionless. So the theoretical yield, we've calculated that in an equation. The actual yield has to be given to you. Or if you're an engineer, you have to determine what's the yield that you can get from your production. And then you can show your supervisor what to expect when you scale it up. And then they run their numbers and say, okay, we can do that, right? Maybe we can improve it over time, but right now we can make money off of that. Or no, that yield is too low, can't do it. Go back to the lab, work on it a little while and try to get the yield up, and then we'll look at it again. So here's a very simple calculation, right? If the theoretical yield for this reaction is 5.6 grams, but the actual yield that you determine is only 4.5 grams, then 4.5 divided by 5.6 times 100 equals 80%. Now, why would it be less? Well, starting from the reaction itself, you could have, you think this is the equation that governs the reaction. Maybe there's a side reaction in there you didn't account for. Maybe that reactant is going someplace else, some of it, okay? Or in the process of running it through your reactor and coming out the other side, you lose some spillage, or maybe you got a leak and it drips out or gases off. Any number of things can reduce your yield. Or the reaction, it just is not that efficient, right? Fritz Haber, when he was working on nitrogen plus hydrogen gas to yield ammonia, let's see, 2 here and 3 there. His yield was only 15%. Right? So he had to figure out, how do I improve my yield? He eventually got it up a lot higher than that with the help of Bosch. Haber and Bosch finally got credit for that reaction. Have I told you that story before? No. This was at the beginning of World War I, right? Just before World War I. And the primary source of nitrates was Chile, because they had hundreds of feet deep of bird guano that had collected on the western side of the Andes. And all you had to do is dig it up and purify it and put it in your explosives, right? So the Western countries embargoed Germany for starting the war. And now they didn't have a supply of nitrates to make their explosives. So Haber and Bosch got together and say, if we make ammonia, then all we have to do is oxidize it. We can make nitrates out of it. And that's how they made their explosives. Just nitrogen from the air. All you need is a cheap source of energy and you can go. So that's the story behind that reaction. Let's see. We got till 11, don't we? Before we have to start. Yeah, okay. So we can do the concept question. Oh, okay. Pennies produced in 1982 were composed of 95% copper. After 1982, the government substituted zinc as the blank, and they just clad the zinc in copper. That's historically speaking, that's called debasing the currency. In other words, now the source of your currency is worth less than it was before. Anyway, on an average, these pennies weighed 3.11 grams. How many atoms of copper were present in one pre-1982 penny? Oh, 1982 is when they started debasing. So it'd be in 1981 or earlier. They did the same thing with silver coins too. They debased them. Some of them you can see, go back and look at some of the older coins, like quarters and half dollars, and turn them on the edge. And you'll see that they're two different metals, right? Two different alloys sandwiched together. I don't know if I got one. If they still doing that way, if they've gotten rid of those. Yep, it's still there. So this side is kind of copper colored and this side is kind of silver colored. Anyway, we want to find out how many atoms of copper were present in the pre-1982 coins. So 3.11 grams is the mass of the coin, but only 95% of it is copper. So I use the decimal equivalent because 95% can't work with that. 0.95 times that, that's the grams of copper. So now we want to find out how many atoms. We need the molar mass, right? Grams on the bottom to cancel. These are with moles. Copper was 60, what was it, 63.55? That gives us the moles. Now the numbers, we have to convert using Avogadro's number. Okay? And that's the thinking part. Grams cancel, moles cancel, leaves us with atoms. So if we do the calculations correctly, we should get 2.8 times 10 to the 22nd atoms of copper. Okay? And the last concept question. Let's see. A 2-liter bottle of carbonated soda has an equivalent average. Get that thing out of the way. 0.20 grams of glucose per 100 milliliters. Glucose is metabolized in the human body according to this equation. And that equation is not balanced. Use the following steps and the associated equations to determine the number of grams of carbon dioxide produced after the consumption of 10 2-liter bottles. Okay, so we balance the equation first. Oops. Yeah, that balanced it. C6 H12O6. Has anybody had anatomy and physiology or biology? They might cover this in biology too. Let's just save ourselves some time. I think it's just 6 and 6. 6, 6. That's balanced. Now, what are we given? Well, we're given 10 2-liter bottles Well, actually, we're given 0.2 grams of glucose per 100 mils. And we need to, let's take it a step at a time. 2 grams of glucose per 100 mils. Right? So first of all, we need to find out how many grams of glucose do we have? We need to convert that to liters. 1 liter. And then how many liters do we actually consume? 20 liters, right? 2 liters times 10 bottles is 20 liters. So that'll get rid of milliliters and liters and leave us with grams. Okay, so we have grams of glucose. Now we want to convert to moles of glucose, because if we have grams of glucose, and the question is grams of CO2. So this is going to give us grams of glucose. Now we need moles of glucose. So we need the molar mass, which is 180. Right? Grams of glucose. Moles of glucose. Now we can convert moles of glucose to carbon dioxide. And the ratio is 1 here and 6 there. Oh, now we need to convert moles of glucose, moles of carbon dioxide to grams of carbon dioxide. And that's 44. Okay, so everything cancels correctly. Here, and it's moles, grams. Okay. And now that's the thinking part, and we just run the numbers. And we should get 59 grams of carbon dioxide after consuming 10 2-liter bottles.